The Milky Way and Andromeda exist today as two separate, fully formed spiral galaxies suspended within the same gravitational neighborhood. They are not drifting randomly through space. They are already bound to each other, locked into a slow and inevitable convergence that has been unfolding for billions of years. At present, the center of Andromeda lies about 2.5 million light-years away from the center of the Milky Way. That distance sounds immense, but on cosmological scales, it is modest. It places both galaxies inside a shared region of influence known as the local group, a collection of galaxies whose motions are dominated not by the expansion of the universe, but by their mutual gravity. This distance is not static, it is shrinking. Careful measurements show that Andromeda is moving toward the Milky Way at roughly 110 kilometers per second, or about 70 miles per second, along our line of sight. This inward motion is detected through its blue shift. The light from Andromeda is slightly compressed as it travels toward us, a clear signature that it is approaching rather than receding. Unlike most distant galaxies, whose light is stretched by cosmic expansion, Andromeda's motion is dominated by local gravity. The expansion of the universe does not meaningfully separate galaxies that are already gravitationally bound on this scale. The motion between the two galaxies is not a straight-line plunge. It is a complex orbital dance governed by the combined mass of both systems and the invisible matter surrounding them. While the radial component of Andromeda's velocity is well measured, the sideways or tangential component is much smaller and harder to detect. Long-term observations using precise astrometry have constrained this sideways motion to be relatively minor. That matters because a large tangential velocity could allow Andromeda to swing past the Milky Way without merging. Instead, the low tangential speed strongly favours a future in which the two galaxies interpenetrate and eventually coalesce. What controls this motion is not just the visible stars and gas of the galaxies themselves. Each galaxy is embedded within an enormous dark matter halo that extends far beyond the bright stellar disk. These halos overlap in influence long before the galaxies visually approach one another. The Milky Way's dark matter halo likely stretches several 100,000 light-years outward, possibly approaching 1,000,000 light-years in diameter. Andromeda's halo is even more massive. Together, these halos dominate the gravitational landscape of the local group. The combined mass of the Milky Way and Andromeda is on the order of several trillion times the mass of the Sun. Most of that mass is dark matter. It does not emit light. It does not collide in the conventional sense, but it exerts gravity relentlessly. This gravity shapes the trajectories of both galaxies and determines their future. The local group itself acts like a shallow gravitational well, with the Milky Way and Andromeda as its two deepest points. Smaller galaxies orbit within this potential, slowly spiraling inward or being slung into elongated paths. Despite the dramatic language often used to describe the future encounter, the present-day configuration is remarkably calm. Nothing in the night sky hints at an impending catastrophe. From within the Milky Way, Andromeda appears as a faint, elongated smudge, visible to the naked eye under dark conditions. Its apparent size on the sky is already several times the diameter of the full moon, but its low surface brightness makes it subtle. Over the next few billion years, that appearance will gradually change, but the pace is glacial by human standards. The reason this encounter unfolds so slowly lies in the nature of gravity over vast distances. Even with trillions of solar masses involved, the separation between the galaxies is so large that the acceleration they exert on each other is weak. Gravity does not pull them together like magnets snapping shut. Instead, it nudges them, year after year, orbit after orbit, drawing them closer in a long, drawn-out process. The timescales involved are measured in billions of years because the distances are measured in millions of light-years. Another reason this is not a sudden crash is that galaxies are not solid objects. They are mostly empty space. The average distance between stars in the Milky Way is several light years. Even in the dense regions of galactic disks, stars are separated by distances so vast that direct collisions between stars during a merger are extraordinarily unlikely. When galaxies interact, it is gravity acting on large-scale distributions of mass that matters, not individual impacts. The present configuration also reflects a long-shared history. The Milky Way and Andromeda did not form independently in isolation and then wander into each other's vicinity by chance. They condensed from the same primordial overdensity in the early universe. Slight variations in density after the Big Bang caused matter to flow inward, forming a growing structure that would eventually fragment into multiple galaxies. The Milky Way and Andromeda are sibling systems, born from the same gravitational seed. As the universe expanded and cooled, these proto-galaxies accumulated gas, formed stars, and developed their familiar spiral shapes. Throughout that process, they remained gravitationally aware of each other. Their mutual attraction slowed their separation relative to the expanding universe and eventually reversed it. While space itself continues to expand on large scales, within the local group, gravity won the competition. The local group gravitational potential acts like a shared basin. Galaxies move within it, much like objects rolling on a gently curved surface. The Milky Way and Andromeda sit near the deepest parts of this basin, slowly drifting toward the lowest energy configuration available to them. That configuration is not two separate galaxies in orbit forever. It is a single, merged system in which orbital energy has been redistributed and dissipated. Energy dissipation in galaxy encounters does not happen through friction in the everyday sense. There is no air resistance, no solid contact. Instead, it occurs through gravitational interactions between vast numbers of particles, stars, gas clouds, and especially dark matter particles. As the galaxies move through each other's halos, they generate gravitational wakes that drag on their motion. This process, known as dynamical friction, steadily drains orbital energy and angular momentum from the system. Even now, long before the visible disks approach, this process is already at work at an extremely subtle level. The overlapping outskirts of the dark matter halos are interacting gravitationally. The effect is weak today, but it sets the stage for what will happen later. Each close approach will amplify this energy loss, tightening the orbit and ensuring that the galaxies do not simply pass by and separate again. From a distance, it might be tempting to imagine the future collision as a single moment in time, a dramatic impact after which everything changes. In reality, the merger is a sequence of events stretched across billions of years. The present-day configuration represents the opening act of that sequence. The galaxies are still far apart, still internally undisturbed, still following orderly rotational motions within their disks. The Milky Way today rotates once every few 100 million years at the Sun's distance from the centre. Andromeda does the same on its own scale. These internal motions are vastly faster than the slow inward drift of the galaxies toward each other. For every kilometre per second of approach speed between the galaxies, stars within each galaxy are orbiting their centres at hundreds of kilometres per second. This contrast in timescales is another reason the merger unfolds gradually. The future is already encoded in the current velocities and positions. If nothing external intervenes, the equations of gravity predict a first close passage in roughly 4 to 5 billion years. That estimate depends on uncertainties in mass distribution and tangential motion, but the overall picture is robust. The galaxies are bound, their relative energy is negative. There is no escape trajectory available under known physics. Yet even that first passage will not mark the end. It will be just one stage in a longer interaction. After passing through each other, the galaxies will slow, turn around, and come back together again, each time losing more orbital energy. Only after multiple encounters will they finally settle into a single, stable structure. Seen from the perspective of the present day, none of this is dramatic. There are no visible shock fronts, no bright flares, no signs of imminent disruption. The Milky Way and Andromeda simply exist, separated by a few million light-years, drifting closer at a speed that would take tens of thousands of years to cross our own galaxy. The scale mismatch between human intuition and cosmic reality makes the process hard to grasp. The present configuration is therefore best understood not as the beginning of a crash, but as a slow gravitational convergence that has already been underway for most of the universe's history. It is governed by mass, distance, and time on scales that dwarf everyday experience. The collision is inevitable, but it is not violent in the way the word suggests. It is patient, structured, and ruled by the quiet mathematics of gravity acting over immense distances. Right now, the Milky Way and Andromeda are still themselves, two spirals, rotating, forming stars, evolving internally. Their future union is written into their motion, but it has not yet reshaped their identities. The sky remains calm, the galaxies remain intact, and the slow approach continues, imperceptible from one generation to the next, unfolding on a timescale that belongs entirely to the universe, rather than to us. The prediction that Andromeda is moving toward the Milky Way is not based on a single observation or a simple extrapolation. It rests on several independent measurement techniques that converge on the same conclusion. The two galaxies are gravitationally bound and approaching one another. The most direct of these measurements comes from spectroscopy, specifically from the Doppler shift of Andromeda's light. When light is emitted from a galaxy, it carries with it a record of motion. If the source is moving away, its spectral lines are shifted toward longer wavelengths, a redshift. If the source is moving toward the observer, those lines are shifted toward shorter wavelengths, a blue shift. This effect is not subtle. It is one of the most precise tools in astronomy, capable of measuring velocities of tens of kilometers per second across millions of light years. Andromeda's spectrum has been studied for over a century. Its absorption lines, produced by stars and gas within the galaxy, are consistently shifted toward the blue. This indicates that Andromeda is approaching the Milky Way rather than receding. The measured radial velocity is about 110 kilometers per second, or roughly 70 miles per second, directed almost straight toward us. This value is corrected for the motion of the Sun around the Milky Way's center and for the Milky Way's own motion within the local group, isolating the true relative motion between the two galaxies. This measurement alone already places Andromeda in a special category. Most galaxies beyond the local group show redshifts, reflecting the expansion of the universe. Andromeda does not. Its blue shift immediately signals that local gravity overwhelms cosmic expansion at this scale. However, radial velocity tells only part of the story. It measures motion directly along the line of sight, not motion across the sky. To know whether Andromeda will collide with the Milky Way or merely pass by, astronomers must also determine its tangential velocity, the sideways component of its motion. This is vastly more difficult to measure. At a distance of about 2.5 million light-years, even a sideways motion of tens of kilometers per second corresponds to an angular shift of only a few micro-arc seconds per year. That is comparable to watching a human hair grow as seen from thousands of kilometers away. The primary tool for constraining this motion has been long-term astrometric observation. By tracking the apparent position of Andromeda's stars against background reference objects over many years, astronomers can measure tiny changes in position. Space-based observatories are essential for this work because they avoid atmospheric distortion and can maintain stable reference frames over long periods. The result of these observations is not a precise sideways velocity, but a tight upper limit. Andromeda's tangential motion appears to be relatively small, on the order of a few tens of kilometers per second at most. This is crucial. If the tangential velocity were large, comparable to or greater than the radial velocity, Andromeda could follow a long, arcing trajectory that misses the Milky Way entirely. Instead, the data indicate that its motion is dominated by the inward radial component. These measurements come with uncertainties, and those uncertainties matter. Astronomers do not claim perfect knowledge of Andromeda's trajectory. The error bars reflect limitations in measurement precision, systematic uncertainties in reference frames, and assumptions about the distribution of mass within both galaxies. Even small uncertainties in velocity, when projected billions of years into the future, can lead to different outcomes. Despite these uncertainties, simulations that incorporate the full range of allowed velocities consistently show a high probability of a merger. Most scenarios lead to a direct collision or a close encounter followed by eventual coalescence. A smaller fraction of simulations produce a near miss, in which the galaxies swing past each other at a distance of several 100,000 light-years. Even in many of those cases, gravitational interactions with their extended dark matter halos still lead to a merger at a later time. The reason the prediction is probabilistic rather than absolute lies in the chaotic nature of gravitational systems over long time scales. The equations governing gravity are deterministic in principle, but small uncertainties in initial conditions can grow over billions of years. This sensitivity does not mean the prediction is unreliable. It means that astronomy acknowledges and quantifies its uncertainties rather than ignoring them. Another layer of complexity comes from the mass distribution within the galaxies. The total mass of the Milky Way and Andromeda is not known exactly. Estimates vary depending on how far their dark matter halos extend and how mass is distributed within those halos. A more massive halo produces stronger gravitational attraction and more efficient energy loss during encounters. A less massive halo produces weaker effects. These differences slightly alter the timing and geometry of the future interaction. The local group itself is also not an isolated two-body system. It contains dozens of smaller galaxies, and their collective mass contributes to the gravitational potential. The most significant of these is the Triangulum galaxy, which may be gravitationally bound to Andromeda and could influence its motion over long timescales. However, these effects are secondary compared to the dominant mass of the two main galaxies. Despite all these caveats, the core observational facts are robust. Andromeda is approaching the Milky Way. Its radial velocity is well measured and significantly inward. Its tangential velocity is constrained to be small enough that escape is unlikely. The combined mass of the two galaxies is sufficient to bind them gravitationally. There is no evidence for any external force or mass concentration that could dramatically alter this trajectory. It is also important to understand what astronomers mean when they say a collision is likely. They are not predicting a sudden impact between two solid objects. They are predicting a gravitational interaction between extended, diffuse systems. Even a scenario that technically counts as a miss can still involve deep overlap of dark matter halos and significant tidal effects on the stellar disks. From a physical perspective, the distinction between a collision and a near miss becomes less sharp at galactic scales. The remaining uncertainty, therefore, does not revolve around whether something significant will happen, but around the exact geometry and timing of the interaction. Will the first close passage occur in 4 billion years or 5? Will the disks pass directly through each other or slightly offset? Will the merger complete in 2 passes or 3? These are the questions that remain open, and they depend sensitively on the small components of motion that are hardest to measure. From a scientific standpoint, this uncertainty is not a weakness. It reflects the limits of measurement and the honesty of the predictive framework. The same methods that predict the Andromeda collision are used to model galaxy interactions throughout the universe, and they have been tested against countless observed mergers at various stages. The physics is well understood. What varies is the input data. As measurement techniques improve, these uncertainties continue to shrink. Longer observational baselines refine proper motion constraints. Improved models of dark matter halos tighten mass estimates. Each refinement narrows the range of possible futures. The overall conclusion has remained stable across decades of study. The Milky Way and Andromeda are on a converging trajectory. What makes this case particularly compelling is that it does not rely on extrapolating from distant analogues alone. It is grounded in direct measurements of our nearest large galactic neighbour. The blue shift is not an inference, it is observed. The small tangential motion is not assumed, it is constrained. The gravitational binding is not speculative. It follows directly from mass estimates and relative velocities. Still, astronomy resists absolute certainty when dealing with events billions of years in the future. The collision probability is high, but not exactly 100%. That remaining uncertainty is a reflection of physical reality, not a gap in understanding. It acknowledges that the universe is not a clockwork mechanism with perfectly known initial conditions, but a dynamic system where precision has limits. In practical terms, the difference between a 90% and a 100% probability has no consequence for the present-day Milky Way. The timescales involved dwarf the lifespan of the Sun, the Earth, and human civilization. What matters scientifically is that we can trace the future of our galaxy using the same physical laws that govern galaxies across the cosmos. The prediction of the Andromeda collision therefore stands as a demonstration of how astronomy connects observation to long-term dynamics. A faint blue shift in a distant galaxy's spectrum, combined with painstaking measurements of tiny positional changes, is enough to map a future billions of years away. The event itself remains far beyond any direct experience, but the evidence for it is already written in the light reaching Earth today. Long before the Milky Way and Andromeda appear to approach one another in any visible sense, their interaction has already begun. The first contact does not involve stars, gas, or luminous structure at all. It occurs in darkness through the gradual interpenetration of their dark matter halos. These halos are the dominant components of both galaxies, vastly larger and more massive than the bright disks that define their visible shapes. A galactic dark matter halo is not a sharp boundary or a compact object. It is a diffuse, extended distribution of mass that surrounds a galaxy in all directions. For a spiral galaxy like the Milky Way, the visible disk extends roughly 100,000 light-years across. The dark matter halo extends several times farther. Estimates place its radius at several 100,000 light-years, and possibly close to 1,000,000 light-years when defined by the region where its gravitational influence remains significant. Andromeda's halo is larger still, reflecting its greater total mass. These halos are not static shells. They are dynamic structures made up of countless dark matter particles moving on intersecting, elongated orbits. They form through hierarchical growth, accumulating material over cosmic time as smaller structures merge into larger ones. By the present day, both the Milky Way and Andromeda sit at the centres of deep gravitational wells, carved primarily by their halos, not by their stars. Because the halos are so large, they begin to interact while the galaxies themselves still appear widely separated. At a centre-to-centre distance of about 2.5 million light-years, the outer regions of the two halos are already within range of each other's gravitational influence. As the galaxies continue their slow approach, these regions increasingly overlap. This overlap marks the true beginning of the merger process. The interaction of dark matter halos is subtle but profound. Dark matter does not collide or dissipate energy through radiation in the way gas does. It passes through itself without shock fronts or compression. Yet it responds to gravity, and gravity alone is enough to reshape the system. When two halos begin to overlap, their particles experience a changing gravitational potential. Orbits that were once stable within a single halo become distorted by the presence of the other. This distortion leads to a process known as gravitational braking. As each galaxy moves through the dark matter environment of the other, it creates a gravitational wake. The moving mass pulls surrounding dark matter particles slightly toward it, creating an overdense region trailing behind. This wake exerts a gravitational pull opposite to the direction of motion, effectively slowing the galaxy down. This mechanism is a form of dynamical friction, but it operates on scales far larger and with constituents far more diffuse than anything encountered in everyday physics. There is no contact force, no viscosity, no material resistance. The friction arises purely from the collective gravitational response of countless particles to a moving mass. Over time, this effect drains kinetic energy from the relative motion of the galaxies and converts it into random motion within the dark matter halos. The importance of this process cannot be overstated. Without dynamical friction, galaxy mergers would be far less efficient. Two galaxies could pass by each other repeatedly without ever settling into a single system. The presence of massive dark matter halos ensures that orbital energy is steadily lost during each encounter, tightening the orbit and drawing the galaxies closer together. In the early stages of the Milky Way-Andromeda interaction, this energy loss is extremely gradual. The density of dark matter in the outer halo regions is low, and the relative velocity between the galaxies is modest. The resulting gravitational wake is faint, and the braking effect is weak. Yet over hundreds of millions and then billions of years, even a weak force becomes significant. As the halos overlap more deeply, the effect strengthens. The density of dark matter increases toward the inner regions of each halo, and the relative motion becomes more strongly coupled to the surrounding mass. Each galaxy begins to feel the other, not as a distant point mass, but as an extended gravitational landscape that reshapes its trajectory. This stage of the merger is invisible in ordinary images. There are no tidal tails, no distorted disks, no bursts of star formation. From the perspective of stars within either galaxy, almost nothing changes. Their local gravitational environment remains dominated by their own galaxy's mass. Yet on the largest scales, the system is already evolving. The halos themselves do not remain unchanged during this process. As they overlap, their shapes become distorted. Initially spherical or mildly triaxial distributions begin to elongate along the axis connecting the two galaxies. The combined gravitational potential becomes asymmetric, and dark matter particles are redistributed into new orbital configurations. This redistribution contributes further to energy loss. Some dark matter particles gain energy and are flung outward into extended orbits, carrying away orbital energy from the system. Others sink deeper into the combined potential well. This exchange of energy and momentum is central to how mergers progress from loose encounters to bound, coalescing systems. The scale of these halos also means that their interaction begins long before any reasonable definition of a collision. By the time the visible disks approach within a few 100,000 light-years of each other, the halos will have been interacting for billions of years. The visible merger is only the late-stage manifestation of a process that started in darkness. From a dynamical standpoint, the halos act as the scaffolding of the merger. They set the timing, geometry, and inevitability of the encounter. The stars and gas respond later, tracing the underlying gravitational evolution rather than driving it. This is why simulations of galaxy mergers are so sensitive to halo properties. Changing the mass, size, or density profile of a halo can dramatically alter the outcome. The Milky Way and Andromeda are particularly effective at merging because both possess massive halos. Their combined mass ensures strong dynamical friction during close passages. Smaller galaxies with lighter halos can orbit larger systems for many billions of years without merging, slowly losing energy but never quite reaching the center. In contrast, two large galaxies of comparable mass are destined to combine. As the halos interact, the relative orbit of the galaxies begins to decay. The initially wide trajectory becomes more tightly bound. The time between successive close approaches shortens. Each passage through the overlapping halo regions extracts more energy than the last. This progressive tightening is what transforms a slow approach into a full merger. The cosmological context of this process is important. Galaxy mergers are not rare or exceptional events. They are a natural consequence of structure formation in a universe dominated by dark matter. Large halos grow by accreting smaller ones, and major mergers between similarly sized halos are key milestones in the evolution of massive galaxies. The Milky Way itself is the product of many such mergers in the past, though most involved much smaller companions. Andromeda shows even clearer evidence of a violent merger history with extensive stellar streams and substructures in its halo. The upcoming interaction between the two galaxies is simply the largest and final major merger in their shared environment. Dynamical friction at these scales operates slowly, but it is relentless. There is no mechanism to reverse it once the galaxies are bound. Energy can be redistributed, but not restored to the organized orbital motion required for separation. The system moves inexorably toward a lower energy configuration. It is important to note that dark matter halos do not merge instantaneously when they overlap. The process is gradual, involving repeated passages and ongoing redistribution. Even after the visible galaxies have merged into a single stellar system, the dark matter halos may retain distinct substructures for some time. Complete relaxation into a single smooth halo can take several billion additional years. Throughout this entire process, the interaction remains governed by gravity alone. There are no shocks, no radiation, no electromagnetic signatures associated with the dark matter itself. Its influence is inferred from motion, from the way galaxies slow, distort, and eventually settle. The silence of dark matter does not imply passivity. It is the dominant actor in the merger. The reason the halos meet first is therefore a simple consequence of scale. They are the largest components of the galaxies, extending far beyond what we see. Their mass dominates the gravitational interaction, and their overlap initiates the mechanisms that make merging inevitable. By the time stars begin to respond dramatically, the outcome has already been decided. In the present epoch, this process is still in its earliest phase. The halos are only beginning to feel each other's presence. The gravitational braking is faint but real. The orbital energy is being drained imperceptibly, setting the stage for future encounters that will reshape both galaxies. From a human perspective, this stage of the merger is abstract and invisible, yet it is the most important phase dynamically. Without it, the Milky Way and Andromeda might simply drift past one another in the distant future. With it, their fates are sealed long before their stars ever meet. The dark matter halos meet first because they are vast, massive, and unavoidable. Their interaction transforms a slow approach into an irreversible convergence. What follows in later stages is built upon this foundation, but the quiet work of gravity in the dark is what makes everything else possible. The first close passage between the Milky Way and Andromeda marks the moment when their long, invisible gravitational courtship becomes visibly dramatic. This encounter is not the final merger, nor is it a sudden catastrophe. It is the first deep interpenetration of two massive galaxies whose dark matter halos have already been interacting for billions of years. Based on current measurements and simulations, this passage is expected to occur roughly 4 to 5 billion years from now, at a time when the Sun itself will be nearing the later stages of its life. This timescale emerges naturally from the present-day configuration. The current separation of about 2.5 million light-years, combined with the measured inward velocity and the gradual loss of orbital energy through dynamical friction, sets a slow countdown. The galaxies do not accelerate rapidly toward one another. Their approach speed increases only modestly as gravity draws them closer. Most of the orbital energy loss happens not during the early approach, but during the first close passage itself. The moment of closest approach, known as pericenter, will not involve the centers of the two galaxies colliding head-on. Instead, simulations suggest a missed distance of tens of thousands of light-years, possibly more, depending on the exact tangential motion and mass distribution. This separation is small compared to the overall size of the galaxies, but large enough that their dense central regions do not immediately merge. Despite this offset, the gravitational consequences will be profound. As the galaxies sweep past one another, tidal forces will act across their entire structures. These forces arise because gravity does not pull equally on all parts of an extended object. The side of each galaxy closer to the other experiences a stronger pull than the far side. The result is stretching, twisting, and distortion on galactic scales. The stellar disks, which today are relatively thin and orderly, will respond dramatically to this tidal stress. Spiral arms will be pulled outward and warped. Portions of the disks will be flung into elongated arcs, extending far into intergalactic space. These are tidal tails, among the most striking features of interacting galaxies observed elsewhere in the universe. Tidal tails are not composed of random debris. They are coherent structures made up of stars and gas that were once part of the galactic disk. Their formation reflects the transfer of angular momentum during the encounter. Some material gains energy and is thrown outward, while other material loses energy and sinks deeper toward the galactic centers. In addition to long tails, the encounter will generate stellar streams. These are narrower filamentary structures formed as stars are pulled from their original orbits and redistributed along the gravitational contours of the interaction. Over time, these streams can wrap around the merging system, forming complex, looping patterns that persist for billions of years. Such features are already seen in other interacting galaxies and in the remnants of past mergers. They are also observed on smaller scales in the Milky Way today, where streams from disrupted dwarf galaxies trace the galaxy's gravitational field. During the first close passage with Andromeda, similar processes will occur on a vastly larger scale. The distortion of the disks will not be uniform. Regions aligned with the direction of motion will be affected differently than those oriented perpendicular to it. The response will also depend on internal structure. Dense central regions resist deformation more effectively than diffuse outer regions. As a result, the outskirts of the disks will be most strongly affected, while the inner regions remain more intact, at least initially. Gas within the disks will respond differently from stars. While stars behave as collisionless particles, gas clouds can interact directly. During the first passage, large-scale gas flows will be induced by tidal torques. Gas will be funneled inward along distorted spiral arms, while other gas will be stripped outward into tidal features. This redistribution of gas sets the stage for enhanced star formation, but that process unfolds over longer timescales and becomes more pronounced after the passage. One of the most common misconceptions about galactic collisions is the idea of stars smashing into each other. In reality, direct stellar collisions are extraordinarily unlikely, even during a close encounter. The reason lies in the sheer emptiness of galaxies. Although they contain hundreds of billions of stars, the distances between those stars are enormous compared to their physical sizes. A typical star like the Sun has a diameter of about 1.4 million kilometers. The average separation between stars in the Milky Way's disk is several light years, which corresponds to tens of trillions of kilometers. Even in the densest regions of galactic disks, stars occupy only a tiny fraction of the available volume. During a merger, the stars from one galaxy pass through the other, much like two swarms of insects passing through each other in open air. Gravity still matters. Stars are deflected from their original orbits, sometimes dramatically, but they do not collide in the everyday sense. Their trajectories are altered by the changing gravitational potential of the combined system, not by direct impacts. This is why galaxy mergers are dynamically violent but not physically destructive to individual stars. The first close passage will therefore reshape the galaxies without destroying their stellar populations. Most stars will survive the encounter unscathed, continuing to shine as they always have, though now on altered orbits. From the perspective of an individual star, the encounter is a slow change in the background gravitational field, rather than a sudden event. The timing of this passage also has broader implications. 4 to 5 billion years from now, the Sun will have grown brighter than it is today, potentially rendering Earth uninhabitable long before the galaxies meet. Human observers will almost certainly not be present to witness the encounter. Yet from a cosmic perspective, the timing is unremarkable. Many galaxies in the universe undergo similar interactions at all epochs. As the Milky Way and Andromeda approach pericenter, their relative velocity will reach several hundred kilometers per second. Even at this speed, the passage will take tens of millions of years to complete. The galaxies do not flash past each other. They slowly interpenetrate, distort, and then begin to separate again, all over a span of time comparable to the age of complex life on Earth. During this phase, the night sky as seen from within either galaxy would change gradually but dramatically. Andromeda would grow from a faint smudge into a sprawling, distorted structure spanning a large fraction of the sky. Star-forming regions, dust lanes, and tidal features would become visible as the two disks overlap. Yet even these changes would unfold over many generations. After the first close passage, the galaxies will not immediately merge. They will continue past one another, reaching a maximum separation smaller than their original distance. This rebound occurs because not all orbital energy is lost in a single encounter. The galaxies overshoot, slow, and then fall back together under gravity. The importance of the first passage lies in how much energy it removes from the system. The strength of tidal distortions and the length of tidal tails are direct indicators of this energy loss. A close, slow passage produces strong distortions and efficient braking. A more distant or faster passage produces weaker effects. Current models suggest a passage close enough to ensure that subsequent encounters are inevitable. This first encounter also leaves lasting imprints. Even if the galaxies temporarily separate afterward, their disks will never fully recover their original structure. Spiral patterns will be disrupted, disks thickened, and stellar orbits heated. The galaxies will carry the scars of the encounter into the next phase of interaction. In this sense, the first close passage represents a point of no return. Before it, the galaxies are largely intact and internally ordered. After it, their futures are irrevocably altered. The interaction has progressed beyond the realm of subtle halo dynamics into visible structural transformation. Yet, it is important to emphasize the contrast between appearance and reality. While the galaxies will look chaotic and distorted during this phase, the underlying process remains governed by smooth gravitational evolution. There is no explosion, no singular moment of impact. The drama is spread across millions of years, driven by the cumulative effect of gravity acting on vast distributions of mass. The first close passage is therefore best understood not as a collision in the everyday sense, but as a deep gravitational encounter. It is the moment when the slow approach becomes visually obvious, when tidal forces sculpt the galaxies into new forms, and when the merger truly enters its active phase. Everything that follows, including the final coalescence into a single galaxy, is shaped by what happens during this initial transformative encounter. When the Milky Way and Andromeda pass through one another for the first time, the most consequential interactions do not involve stars. They involve gas. Stars behave as nearly collisionless particles, responding smoothly to gravity and rarely coming close to one another. Gas clouds, by contrast, occupy extended volumes, carry pressure, and interact through direct physical contact. During a galactic encounter, it is the interstellar medium that absorbs the violence of the collision and converts orbital motion into heat, turbulence, and new generations of stars. Each galaxy contains vast reservoirs of gas, threaded through its disk and halo. In the Milky Way, the interstellar medium exists in multiple phases: cold molecular clouds, cool atomic hydrogen, warm ionized gas, and hot diffuse plasma. These components are unevenly distributed, concentrated in spiral arms, and layered above and below the galactic plane. Andromeda contains similar structures, though with different proportions and distributions. During the first close passage, these gaseous systems do not simply pass through one another unaffected. As the two disks interpenetrate, gas clouds from one galaxy encounter gas clouds from the other at relative velocities of hundreds of kilometers per second. Unlike stars, gas clouds cannot pass through each other freely. Their atoms interact electromagnetically, producing shocks, compression, and dissipation of kinetic energy. The collision between galaxies therefore becomes, at its core, a collision between gaseous media. One of the first consequences of this interaction is the formation of large-scale shock fronts. Where gas flows converge, the sudden deceleration produces sharp increases in temperature and pressure. These shocks propagate through the interstellar medium, heating gas to millions of degrees and generating intense turbulence. The gas does not settle immediately. It becomes chaotic, stirred by competing flows, shearing motions, and pressure gradients. This turbulence has a dual effect. On small scales, it can disrupt fragile structures, tearing apart diffuse clouds and redistributing material across the disk. On larger scales, it can compress gas efficiently. Compression is the key ingredient for star formation. When gas density increases beyond a critical threshold, gravity can overcome internal pressure and initiate collapse. The merger therefore creates ideal conditions for triggering star formation across vast regions. The compression is not localized to a single point. It occurs along distorted spiral arms within tidal bridges and in the central regions of the galaxies where gas is funneled inward by gravitational torques. As angular momentum is redistributed, large quantities of gas lose support against gravity and flow toward the galactic centers. These inflows dramatically increase central gas densities. In these environments, star formation proceeds rapidly. Massive clusters of young stars ignite within a relatively short time, producing intense ultraviolet radiation and stellar winds. The collective output of these stars illuminates the surrounding gas, creating bright emission regions visible across intergalactic distances. This is one of the reasons interacting galaxies often appear unusually luminous. The scale of this star formation is unlike anything seen in isolated galaxies. Instead of being confined to spiral arms or localized regions, it can span tens of thousands of light years. Entire disks can experience elevated star formation rates simultaneously. In some regions, star formation may increase by an order of magnitude compared to pre-encounter levels. Despite this activity, the process is not explosive in a destructive sense. The energy released by newborn stars and supernovae is spread across immense volumes of space. Individual planetary systems are rarely affected directly. The increased radiation does not sweep through galaxies as a lethal wave. Instead, it is diluted by distance and absorbed locally by gas and dust. The shock-heated gas itself emits strongly at high energies, particularly in X-rays. Observations of interacting galaxies elsewhere show extended halos of hot gas generated by merger-induced shocks and stellar feedback. These halos can persist for hundreds of millions of years, gradually cooling and raining material back into the system or escaping into intergalactic space. Another important consequence of gas collisions is the generation of large-scale turbulence. Turbulent motion prevents gas from settling quickly into stable disks. It maintains high pressure and chaotic flows, delaying the return to orderly rotation. This turbulence also broadens the range of densities within the gas, creating both extremely dense star-forming regions and diffuse, heated reservoirs that resist collapse. The night sky within such a system would grow brighter, not more dangerous, because light travels far more efficiently than destructive energy. The probability of a star or planet being struck by dense gas or debris remains negligible. Even in regions of intense star formation, the average density of material is still extraordinarily low by terrestrial standards. Radiation levels would increase locally near starburst regions, but stars are separated by vast distances. The majority of stellar systems would experience only a gradual brightening of the surrounding galaxy, not direct exposure to harmful conditions. The merger enhances luminosity, not lethality. This distinction is often misunderstood. The word collision suggests impact, damage, and destruction. On galactic scales, collision instead means interaction. Gas clouds collide, dissipate energy, and reorganize matter. Stars respond to gravity. The system as a whole becomes more luminous because gravitational energy is converted into radiation through gas dynamics and star formation. The triggered star formation also has a finite lifespan. Gas reservoirs are not infinite. As stars form rapidly, they consume available cold gas. At the same time, stellar winds and supernova explosions inject energy back into the interstellar medium, heating it and driving outflows. These feedback processes eventually suppress further star formation by removing or stabilizing the remaining gas. During the first close passage, however, the balance favors ignition rather than suppression. The compression from tidal forces and shocks overwhelms stabilizing mechanisms. The result is a prolonged but temporary increase in star formation that can last several 100 million years. The brightest phases do not occur instantaneously at pericenter. There is a delay as gas responds to tidal torques, flows inward, cools, and collapses. This delay means that peak luminosity may occur after the galaxies have already begun to separate again. The visual drama therefore lags behind the dynamical encounter. In tidal tails and bridges, gas can also collapse into new, self-gravitating systems. These regions may form tidal dwarf galaxies, small stellar systems born from stripped material rather than primordial collapse. Such objects are transient on cosmic timescales, but they demonstrate how mergers can create structure as well as destroy it. From within the Milky Way, the sky during this phase would be transformed. Andromeda's distorted disk and luminous star-forming regions would dominate large portions of the sky. Dust lanes, glowing nebulae, and extended tidal features would be visible, slowly evolving over millions of years. The brightness increase would be gradual, unfolding over many generations. Importantly, this brightness does not correspond to increased danger. Supernova rates would rise modestly, but supernova remain rare events on galactic scales. The chance of a nearby supernova affecting a given planetary system remains extremely small. Most stars would continue their lives unaffected by the increased activity elsewhere in the galaxy. The gas collisions therefore act as the engine of visible change. They convert the ordered motion of two rotating disks into heat, light, and new stars. They shape the appearance of the merger and determine much of its observable character. Without gas, the merger would still occur, but it would be far quieter, marked mainly by stellar redistribution rather than luminous activity. As the first close passage concludes, much of the gas will be redistributed into new configurations. Some will be consumed in stars, some heated into diffuse halos, some expelled into intergalactic space. What remains will influence later stages of the merger, including subsequent passages and the final coalescence. The crucial point is that the most physically collisional component of galaxies is not the stars, but the interstellar medium. Gas clouds interact directly, producing shocks and compression that reshape the galaxies from within. This process makes mergers spectacular to observe while remaining surprisingly gentle to the individual stars that inhabit them. The night sky grows brighter because gravity channels energy into radiation through gas dynamics and star formation. It does not grow deadlier because the scales involved dilute that energy across vast distances. The merger transforms galaxies, not by smashing their contents together, but by reorganizing matter through the slow, relentless physics of gravity and fluid interaction. The Milky Way's spiral structure is not a rigid framework etched permanently into the galaxy. It is a dynamic pattern, maintained by a delicate balance between gravity, rotation, and the collective motion of stars and gas. Spiral arms are not solid objects that stars move along. They are density waves, regions where matter temporarily bunches together as it orbits the galactic center. This structure is stable only as long as the gravitational environment remains relatively smooth and symmetric. The first close passage with Andromeda disrupts that symmetry on every scale. As Andromeda approaches and then sweeps past, the Milky Way experiences a rapidly changing gravitational field. This change is slow by human standards, but fast compared to the timescale on which spiral patterns are maintained. The tidal forces exerted across the Milky Way's disk distort the gravitational potential that sustains the spiral arms. The result is destabilization. Spiral density waves lose coherence as stars are pulled out of their regular orbital alignments. Initially, the spiral arms become asymmetric. One side of the galaxy experiences stronger tidal stretching than the other, producing lopsided arms and irregular pitch angles. Arms that were once evenly spaced begin to fragment, twist, or merge. Some segments are stretched outward into tidal features, while others are driven inward toward the central regions. This destabilization is not instantaneous. Over several 100 million years surrounding the first close passage, the spiral pattern becomes increasingly disordered. The familiar grand design appearance of the Milky Way fades, replaced by a more chaotic, flocculent structure. Spiral arms lose their identity as long-lived features and become transient, short-lived overdensities that form and dissolve under tidal stress. Gas plays a crucial role in this transformation. As tidal forces redistribute angular momentum, gas is driven away from the disk plane and toward the galactic center. The loss of gas from the arms weakens their contrast and reduces their ability to sustain star formation. Without continuous reinforcement from gas dynamics, the arms cannot re-establish themselves in their original form. At the same time, the stellar disk begins to thicken. In the present-day Milky Way, most stars orbit within a relatively thin plane, with vertical motions that are small compared to their circular velocities. This thinness is a consequence of long-term dynamical cooling, where stars settle into orderly orbits. The encounter with Andromeda reverses this process. Tidal forces inject energy into stellar orbits. Stars are pulled slightly above and below the galactic plane, increasing their vertical velocities. Each closed gravitational perturbation adds to this effect. The disk responds by puffing up, becoming thicker and less sharply defined. What was once a thin, flattened structure evolves into a more vertically extended distribution of stars. This thickening is not uniform. Outer regions of the disk are affected first, and most strongly because they are less tightly bound to the galactic center. Inner regions resist vertical heating more effectively, but are not immune. Over time, even stars near the Sun's present orbital radius would experience increased vertical motion, contributing to a thick disk population. As the disk thickens, its ability to support spiral structure diminishes further. Thin disks favour the formation of coherent density waves. Thick disks damp them. The combined effect of tidal disruption and vertical heating accelerates the dissolution of spiral arms, pushing the Milky Way away from a spiral identity. Another major structural change involves the formation and evolution of a central bar. Even before the encounter, the Milky Way hosts a bar-like structure at its center, composed of stars on elongated orbits. The interaction with Andromeda strengthens this feature dramatically. Tidal torques redistribute angular momentum, driving stars into more eccentric, elongated paths aligned with the galaxy's inner potential. As gas is funneled inward, the central mass concentration increases, reinforcing the bar. The bar grows longer and more massive, extending farther into the disk. Its rotation slows as it transfers angular momentum outward, further altering the dynamics of the surrounding stars. The bar itself becomes a driver of instability. It channels gas toward the center, feeds star formation, and excites resonances that scatter stars onto new orbits. In combination with Andromeda's tidal influence, the bar helps erase the remaining orderly rotation of the disk. Warping also becomes pronounced. Even before the merger, the Milky Way's disk is slightly warped at large radii, likely due to interactions with satellite galaxies and misalignment between the disk and the dark matter halo. The passage of Andromeda amplifies this effect dramatically. The disk bends and twists, no longer lying in a single plane. This warp is not static. Different regions of the disk precess at different rates under the combined gravitational influences of the Milky Way's halo and Andromeda's passing mass. The result is a complex, time-varying shape, with the disk resembling a distorted, rippling sheet rather than a flat plate. As these structural changes accumulate, the nature of stellar motion within the Milky Way fundamentally changes. In the present galaxy, most stars follow nearly circular orbits around the centre, with small random deviations. This ordered rotation defines the disk and underpins its spiral structure. The merger disrupts this order. Tidal forces and repeated perturbations scatter stars onto more eccentric and inclined orbits. Angular momentum is redistributed, and the clear separation between disk and halo populations blurs. Stars that once moved coherently in the disk begin to occupy a wider range of orbital orientations. This transition from ordered rotation to chaotic motion does not mean randomness in a literal sense. The stars still obey gravity and move on predictable trajectories. What changes is the simplicity of those trajectories. Instead of nearly circular orbits confined to a plane, stars follow elongated, tilted paths that take them far above and below the former disk. The velocity distribution becomes hotter, meaning that random motions become comparable to rotational motion. In such a system, rotation no longer dominates the dynamics. The galaxy begins to resemble a pressure-supported structure rather than a rotation-supported disk. This process unfolds over multiple passages, but the first close encounter initiates it decisively. After this passage, the Milky Way cannot return to its original spiral form. Even if some spiral-like features reappear temporarily, they are weak and short-lived. The fundamental conditions that sustained a spiral disk are gone. The fate of the spiral structure is therefore sealed not by a single event, but by the cumulative effect of tidal heating, angular momentum transfer, and gravitational asymmetry. The Milky Way transitions from a thin, rotating disk with well-defined arms into a thicker, more chaotic stellar system. From within the galaxy, this transformation would be subtle on short timescales. No star would suddenly change course. No structure would vanish overnight. Over tens and hundreds of millions of years, however, the changes would be unmistakable. The sky would lose the regularity imposed by spiral arms and gain a more diffuse, three-dimensional appearance. In the long run, this evolution sets the stage for the final merger. By erasing the disk and its ordered rotation, the encounter prepares the Milky Way to merge smoothly with Andromeda into a single, more spheroidal system. The destruction of spiral structure is not a side effect. It is a necessary step in the transformation from two rotating disks into one merged galaxy. The Milky Way's spiral arms, which today define its identity, are therefore temporary features on cosmic timescales. They persist only as long as the galaxy remains dynamically cold and isolated. The encounter with Andromeda ends that isolation. What follows is not destruction in the catastrophic sense, but reorganization. The galaxy does not disappear. It changes state, trading order for complexity as gravity reshapes it into something new. Andromeda does not enter the encounter with the Milky Way as a passive partner. It is the more massive of the two galaxies, with a larger stellar disk, a more extensive halo, and a longer history of significant mergers already written into its structure. When the first close passage occurs, Andromeda's internal response reflects both its greater mass and its prior dynamical complexity. The same tidal forces that distort the Milky Way act on Andromeda as well, but they do so on a system that is already less orderly and more dynamically evolved. One of the earliest and most persistent effects is the development of strong structural asymmetries. Even before the encounter, Andromeda's disk is not perfectly symmetric. Observations already reveal warps, off-center rings, and kinematic irregularities, likely the remnants of past interactions with satellite galaxies. The tidal field generated by the Milky Way amplifies these pre-existing features rather than creating distortions from a pristine baseline. As Andromeda approaches pericenter, the side of its disk facing the Milky Way experiences a stronger gravitational pull than the far side. This differential force stretches the disk along the interaction axis. Spiral arms become uneven in strength and curvature, with some arms drawn outward into tidal features while others are compressed inward. The disk becomes lopsided, with its mass distribution shifted away from the galactic center. These asymmetries are not confined to the stellar component. The gas disk responds even more strongly. Gas is less tightly bound than stars and more sensitive to changes in the gravitational potential. As tidal torques act on Andromeda, angular momentum is redistributed within the disk. Gas loses angular momentum efficiently and begins to drift inward. This inward gas flow is one of the most important internal responses of Andromeda during the encounter. Tidal torques exerted by the Milky Way and by Andromeda's own distorted stellar bar funnel gas from large radii toward the central kiloparsecs. The process is gradual but sustained, operating over hundreds of millions of years around the time of closest approach. As gas accumulates in the inner regions, its density rises sharply. Cooling processes allow it to lose thermal energy, further enhancing collapse. The central molecular gas reservoir grows far beyond its pre-encounter state. Under these conditions, star formation becomes highly efficient. The result is the possibility of a central starburst. A starburst is not a single explosive event, but a phase of elevated star formation lasting tens to hundreds of millions of years. In Andromeda's case, the starburst would be concentrated toward the core, where gas densities and pressures reach their highest values. Massive star clusters form in rapid succession, producing intense radiation fields, strong stellar winds, and frequent supernova explosions. Whether Andromeda experiences a dramatic starburst or a more moderate increase in star formation depends on several factors. The total gas content of the galaxy at the time of encounter is critical. Andromeda today contains less cold gas relative to its stellar mass than the Milky Way. This suggests that its starburst may be less extreme than those seen in very gas-rich mergers, but still significant on galactic scales. Feedback from newly formed stars plays a regulating role. As massive stars evolve and explode, they inject energy and momentum into the surrounding gas. This feedback heats the gas and can drive outflows, limiting the duration and intensity of the starburst. In Andromeda, with its deeper gravitational potential, gas is harder to expel completely, allowing some recycled material to fall back toward the center and sustain star formation over longer timescales. Structural asymmetries extend beyond the disk and into the halo. The dark matter halo of Andromeda becomes elongated and distorted as it overlaps with the Milky Way's halo. This distortion feeds back into the visible galaxy by altering orbital families within the disk and bulge. Stars that once followed relatively regular paths are scattered onto more eccentric or inclined orbits. The bulge of Andromeda responds differently from its disk. Being more centrally concentrated and pressure-supported, it resists deformation more effectively. However, it is not immune. The changing gravitational potential can induce triaxiality in the bulge, making it elongated rather than spherical. This triaxial shape further facilitates gas inflow by providing non-axisymmetric gravitational torques. Bars and oval distortions become more prominent under these conditions. Even if a strong bar does not fully develop, weaker non-axisymmetric features are enough to channel gas inward. These structures evolve over time, strengthening during close passage and weakening as the galaxy moves away, only to be reinforced again during subsequent encounters. Comparing the internal response of Andromeda to that of the Milky Way highlights the importance of mass dominance. Andromeda is the more massive system, with a total mass perhaps 1.5 to 2 times that of the Milky Way, depending on halo estimates. This mass difference affects how each galaxy absorbs and responds to tidal energy. Because Andromeda's gravitational potential is deeper, its disk is more resistant to complete disruption during the first passage. While the Milky Way's spiral structure is rapidly destabilized, Andromeda may retain recognizable disk features for longer. Its greater mass also means that it exerts stronger tidal forces on the Milky Way than it experiences in return, especially in the early stages. This asymmetry influences the geometry of the encounter. Andromeda acts as the dominant perturber, shaping the Milky Way's response more strongly than the reverse. However, dominance does not imply immunity. The Milky Way's mass is still sufficient to significantly perturb Andromeda, particularly in its outer disk and halo. The mass difference also affects orbital decay. Dynamical friction operates more efficiently on the less massive object moving through a more massive halo. As a result, the Milky Way loses orbital energy slightly faster than Andromeda. This contributes to the gradual sinking of the Milky Way deeper into the combined gravitational potential over successive passages. Internally, Andromeda's stars experience less dramatic heating per unit mass than those in the Milky Way, but the effect is spread across a larger system. Over time, the cumulative heating thickens Andromeda's disk and reduces the contrast between disk and halo populations. Ordered rotation becomes less dominant, especially in the outer regions. The response of Andromeda is also shaped by its merger history. Evidence suggests that Andromeda underwent a major merger several billion years ago. This prior event likely left its disk dynamically hotter and its halo rich in substructure. Such a system responds differently to new perturbations than a dynamically cold, undisturbed disk. In practical terms, this means that Andromeda's response may appear less dramatic in some respects and more complex in others. Its disk may not fragment as cleanly into tidal tails, but it may produce more diffuse, extended stellar debris. Its gas inflows may be more centrally concentrated, leading to a brighter but more compact starburst. As the first close passage concludes, Andromeda carries lasting internal changes forward into the next phase of the interaction. Its mass distribution has shifted, its gas reservoir has been rearranged, and its stellar orbits have been heated. Even if some disk-like structure persists, it is no longer the same galaxy it was before the encounter. Over longer timescales, these internal responses accumulate. Subsequent passages reinforce asymmetries, drive further gas inflow, and continue to erode ordered rotation. The distinction between disk, bulge, and halo becomes less clear as stars are redistributed throughout the system. The comparison between Andromeda and the Milky Way during this phase underscores a key principle of galaxy mergers. Mass matters, but it does not confer stability in the long run. The more massive galaxy may dominate the early interaction, but it is ultimately transformed alongside its smaller companion. The encounter does not produce a winner and a loser, it produces a new system shaped by the combined histories and responses of both. Andromeda's internal response therefore plays a central role in determining the character of the final merged galaxy. Its mass, structure, and gas content bias the outcome toward a massive, spheroidal remnant rather than a rebuilt spiral. The asymmetries, inflows, and starbursts initiated during the first close passage are not transient curiosities. They are steps in a long reconfiguration that ends only when the two galaxies become one. After the first close passage, the Milky Way and Andromeda do not settle immediately into a single unified galaxy. Instead, they separate again, drawn apart by the momentum they still retain. This retreat marks the beginning of a new phase in the interaction, defined by oscillating orbits rather than a single decisive encounter. The galaxies move away from one another, slow under mutual gravity, and then reverse course. What follows is a sequence of returns, each one bringing them closer, more deeply entangled, and less distinct. The orbit after the first encounter is no longer the wide, gentle trajectory that characterized the initial approach. Orbital energy has been lost through dynamical friction, tidal heating, and the redistribution of mass within both galaxies and their halos. As a result, the separation reached after the first rebound is smaller than the original distance. The galaxies never again return to their pre-encounter configuration. This oscillatory motion is a natural consequence of gravity acting on extended, massive systems. The galaxies overshoot their mutual center of mass because energy dissipation during the first passage is significant but incomplete. They remain bound, but not yet merged. The result is a decaying orbit, with each oscillation losing more energy than the last. The timescale between the first and second passages is measured in billions of years. Gravity is strong, but the distances involved are immense and the systems are diffuse. The galaxies must travel hundreds of thousands of light years outward and back inward again. Even at velocities of several hundred kilometers per second, such journeys take vast amounts of time. During this interval, the internal structures of both galaxies continue to evolve. The tidal distortions induced during the first passage do not disappear when the galaxies separate. Stellar streams, tidal tails, and warped disks persist, gradually stretching and dispersing under the combined gravitational field. The galaxies are no longer isolated entities, but components of a shared, evolving system. As the galaxies fall back toward one another for the second passage, their relative velocity is typically lower than during the first encounter. This slower approach enhances the effectiveness of dynamical friction. The overlapping dark matter halos interact more strongly, producing larger gravitational wakes and more efficient braking. Each galaxy plows through an increasingly dense background of matter associated with the other. The second close passage therefore tends to be more destructive to ordered structure than the first, despite involving less orbital energy overall. The reduced speed allows tidal forces to act for longer periods, giving them more time to distort stellar orbits and redistribute mass. Disks that survived the first encounter in a recognizable form are further thickened and disrupted. Energy dissipation during these later passages occurs through the same mechanisms as before, but with greater intensity. Dynamical friction in the dark matter halos continues to drain orbital energy. Tidal heating increases random motions within the stellar components. Gas interactions generate further shocks and turbulence, though the available gas reservoir may already be reduced by earlier star formation and outflows. This ongoing dissipation explains why the merger does not complete after a single encounter. The system sheds energy incrementally. There is no efficient mechanism to remove all orbital energy at once without direct dissipative collisions between massive components. Instead, energy is transferred step by step from coherent orbital motion into internal motions of stars and dark matter. As the galaxies pass through each other repeatedly, the degree of overlap and mixing increases. Stellar populations that were once clearly associated with one galaxy or the other become intermingled. Orbits cross and recross the combined potential well, erasing clear boundaries. Over time, it becomes increasingly difficult to define which stars originated in which system based solely on their present-day positions. The dark matter halos also merge progressively. Substructures within each halo are stripped, stretched, and redistributed. While the halos may retain identifiable components for some time, their mass distributions become more similar with each pass. The combined halo grows smoother as orbital memory is lost. Gas, if still present in significant amounts, continues to respond dissipatively. Inflows toward the central regions may be reignited during each passage as tidal torques are renewed. However, the overall gas fraction declines over time. Star formation and feedback deplete cold gas, reducing the intensity of later starbursts. The merger becomes increasingly dominated by stellar and dark matter dynamics. The oscillatory nature of the orbit is also influenced by angular momentum transfer. Angular momentum is not destroyed, it is redistributed. Some is transferred from the orbital motion of the galaxies into internal rotation, random motion, and the outer regions of the merged halo. Tidal tails and escaping material carry angular momentum away from the central system, allowing the core to settle into a more compact configuration. Despite strong gravity, the merger takes so long because gravity alone does not provide a rapid dissipation mechanism. In everyday collisions, kinetic energy is quickly converted into heat through direct contact and friction. In galactic encounters, most of the mass is collisionless. Stars and dark matter interact only through long-range forces, which act gently over time rather than abruptly. The vast scale of the system further stretches the timeline. Even when the galaxies are deeply interpenetrating, their characteristic sizes are hundreds of thousands of light years. Crossing times, the times it takes for matter to traverse the system, are measured in hundreds of millions of years. Several such crossings are required for the system to relax into equilibrium. Chaotic dynamics also play a role. As the gravitational potential changes during each passage, stellar orbits become increasingly complex. Some stars gain energy and are flung onto wide looping paths. Others lose energy and sink deeper into the core. This chaotic mixing, known as violent relaxation, is efficient at redistributing energy, but still requires multiple dynamical times to complete. The second and third passages are therefore not redundant repetitions of the first. Each encounter operates on a system that has already been altered. The galaxies are less ordered, more overlapping, and more responsive to further perturbation. The identity of each galaxy fades progressively with each pass. By the time the third passage occurs, the system is often better described as a single, highly disturbed galaxy with two dense cores, rather than as two separate galaxies. The relative separation at apocenter becomes small, and the motion between the cores slows dramatically. Orbital decay accelerates because the cores move within a shared, dense environment. Eventually, the oscillations damp out. The galaxies no longer separate into distinct entities after each pass. Instead, they settle into a common center of mass. The transition from oscillating orbits to final coalescence marks the end of the merger as a multi-stage process and the beginning of the remnant's long-term evolution. The length of this process underscores a central lesson of galactic dynamics. Strong gravity does not guarantee rapid change. When acting on enormous, diffuse systems, gravity produces slow, cumulative evolution rather than instantaneous transformation. The merger of the Milky Way and Andromeda is not delayed because gravity is weak, but because it is acting on scales where even strong forces require immense time to do their work. From start to finish, the merger spans several billion years. The second and third passages occupy much of this timeline, gradually erasing structure, redistributing energy, and blending the two galaxies into one. What appears from a distance as a dramatic collision is, in reality, a prolonged process of orbital decay and mixing, governed by the patient, unyielding nature of gravity acting across cosmic distances. The fate of the solar system during the merger between the Milky Way and Andromeda is one of the most frequently misunderstood aspects of the event. Popular imagery often suggests catastrophic disruption, stars flung violently through space, and planetary systems torn apart. In reality, the solar system's experience will be governed by probabilities, vast distances, and the smooth action of gravity. The merger dramatically reshapes galaxies, but it does so in a way that is surprisingly gentle to individual stars and their planetary systems. The first question is whether the Sun's orbit around the galactic center is likely to be significantly perturbed. The answer is yes, but not in a sudden or destructive way. As the Milky Way's disk is distorted, thickened, and eventually dissolved into a more spheroidal structure, stars throughout the galaxy experience changes in their orbits. The Sun is no exception. Its current near-circular path, roughly 27,000 light-years from the galactic center, is a temporary configuration tied to the existence of a thin, rotating disk. During the merger, the gravitational potential of the Milky Way changes repeatedly and non-uniformly. Each close passage with Andromeda alters the mass distribution of the combined system. These changes slowly modify stellar orbits through a process known as gravitational scattering. The Sun's orbit may become more eccentric, more inclined, or both. Over billions of years, it is likely to drift away from the plane of the original Milky Way disk, as that plane itself loses meaning. Despite this, the probability of a close encounter with another star remains extraordinarily low. Even during the densest phases of the merger, the average separation between stars is measured in light years. The Sun's gravitational sphere of influence is tiny compared to the volume of space it occupies. Direct stellar flybys close enough to disrupt planetary orbits are exceedingly rare. Statistical studies of galaxy mergers show that planetary systems are overwhelmingly preserved. The more realistic concern is not disruption, but relocation. The Sun is likely to end up on a different orbit within the merged galaxy than the one it occupies today. Simulations suggest that a significant fraction of stars from the Milky Way are displaced to larger galactocentric distances after major mergers. Some are scattered outward into the stellar halo of the remnant, while others sink slightly inward depending on how they exchange energy with the evolving gravitational field. The likelihood of complete ejection from the galaxy exists, but it is small. To escape entirely, the Sun would need to gain enough kinetic energy to exceed the escape velocity of the merged system. This typically requires a strong gravitational interaction, such as a close passage near the dense core of the other galaxy, or a multibody encounter involving massive objects. For a star on a relatively ordinary orbit like the Sun's, such interactions are statistically unlikely. Most scenarios place the Sun remaining bound to the final merged galaxy, but on a more distant and less ordered orbit. It may find itself tens or even hundreds of thousands of light-years from the center, moving on a slow, elongated path through a diffuse stellar environment. Alternatively, it may remain closer to the core, but on a highly inclined orbit that takes it far above and below any residual disk-like structure. In either case, the solar system remains intact. Planetary orbits are governed primarily by the Sun's gravity, which overwhelmingly dominates over galactic tidal forces at the scale of the solar system. Even dramatic changes in the Sun's galactic orbit have negligible direct effect on the stability of planets. The solar system has already survived billions of years of galactic evolution, including passages through spiral arms and encounters with molecular clouds, without disruption. The night sky, however, would change profoundly, assuming any observer remains capable of seeing it. As Andromeda approaches and then passes through the Milky Way, it gradually grows from a faint smudge into a dominant feature. During the first close passage, its distorted disk, bright star-forming regions and tidal structures would stretch across a large fraction of the sky. The sky would be richer, brighter, and more complex than anything seen today. After the first passage, as the galaxies separate and then return, the sky continues to evolve. Tidal tails and stellar streams populate the heavens with faint arcs of light. The concept of a single, well-defined galactic band, like the Milky Way we see today, begins to break down. Instead, the sky becomes filled with overlapping structures from both progenitor galaxies. By the time of the later passages, the distinction between Milky Way stars and Andromeda stars loses meaning. The sky would contain stars on a wide range of orbits, forming a more isotropic distribution. The night sky would appear less dominated by a single bright plane and more filled with diffuse starlight in all directions. Importantly, this increase in brightness does not correspond to an increase in danger. The additional light comes primarily from distant stars and star-forming regions spread across vast volumes. Radiation intensity at the location of the solar system remains low. Even during starburst phases elsewhere in the merging galaxies, the energy output is diluted by distance. Supernova rates increase modestly during mergers, but the probability of a nearby supernova affecting Earth or its successors remains extremely small. Most supernovae occur thousands of light years away. Their effects are local, not galaxy-wide. The merger enhances the visual drama of the sky without imposing widespread hazards. The long-term orbital stability of the solar system within the merged galaxy depends on how the remnant relaxes. After the final coalescence, the combined system undergoes a period of violent relaxation during which stellar orbits are redistributed into a stable configuration. Once this phase ends, the gravitational potential becomes smoother and more static. At that point, the Sun's orbit stabilizes again, though it bears little resemblance to its original state. Instead of orbiting in a thin disk, it likely moves within a spheroidal or weakly rotating stellar distribution. The orbital period may lengthen significantly, potentially spanning several billion years per revolution. This environment is not inherently unstable. Elliptical and spheroidal galaxies host countless stars on such orbits for trillions of years. The solar system's long-term survival is therefore not threatened by the merger itself. The dominant threats to the solar system's future remain local and stellar in nature, such as the Sun's own evolution into a red giant rather than galactic dynamics. It is also important to consider timing. The merger unfolds over a period comparable to the remaining main sequence lifetime of the Sun. By the time the most dramatic phases occur, Earth is likely to be uninhabitable due to increasing solar luminosity. Any future observers witnessing the merger would not be human, and may not even be biological in any familiar sense. From a purely dynamical perspective, the solar system behaves like a tracer particle within a vast gravitational field. It follows the evolving potential without strongly influencing it. Its fate is determined statistically rather than deterministically. There is no single predicted path, only a distribution of likely outcomes. What all plausible outcomes share is continuity rather than catastrophe. The solar system is not torn apart. It is not flung violently into intergalactic space in most scenarios. It drifts slowly and gently into a new galactic context. The merger of the Milky Way and Andromeda transforms galaxies, not planetary systems. It rearranges stars on grand scales while leaving the fine structure of systems like the solar system largely untouched. The Sun's future orbit will differ from its present one, and the sky above it will change beyond recognition. But the underlying stability of the solar system persists. In that sense, the fate of the solar system mirrors the broader truth about galactic mergers. They are events of enormous scale and duration, governed by gravity acting patiently over billions of years. Their violence is collective and structural, not local and destructive. For individual stars and their planets, the merger is not an apocalypse, but a long migration through an evolving cosmic landscape. At the heart of both the Milky Way and Andromeda lie supermassive black holes, compact objects whose masses rival those of entire star clusters. In the Milky Way, this object is Sagittarius A star, with a mass of about 4 million times that of the Sun. Andromeda's central black hole is far larger, with an estimated mass on the order of 100 million solar masses. These black holes dominate the dynamics of their immediate surroundings, but on galactic scales they are small players, carried along by the motion of the galaxies that host them. During the early stages of the merger, the two black holes are simply passengers. As the Milky Way and Andromeda pass through one another and then separate again, each black hole remains embedded in the dense stellar and dark matter environment of its host galaxy's core. Their separation mirrors the separation of the galactic centers, shrinking gradually with each passage as orbital energy is lost. The moment when the black holes begin to interact directly occurs much later, after repeated encounters have drawn the two galactic cores into close proximity. By this stage, the distinction between the Milky Way and Andromeda as separate galaxies has largely disappeared. What remains is a single, massive, highly disturbed stellar system containing two dense nuclei, each centered on a supermassive black hole. As these nuclei move within the shared gravitational potential, dynamical friction becomes extremely efficient. Dense concentrations of stars and dark matter surround each black hole, and as each core moves, it generates a gravitational wake that drags against its motion. This process steadily removes orbital energy, causing the two black holes to spiral toward one another. Eventually, the separation shrinks to a few tens of parsecs. At this point, the two black holes form a bound binary system. They orbit a common center of mass, embedded in a dense environment of stars and gas. This marks a fundamental transition. The black holes are no longer merely following the galaxy's merger. They are now engaged in a merger of their own. The formation of a supermassive black hole binary is a robust prediction of galaxy merger theory. Observations of other galaxies provide indirect evidence for such systems, including disturbed nuclear kinematics and periodic emission signatures. In the case of the Milky Way and Andromeda, the mass disparity between the two black holes means that the center of mass of the binary lies much closer to Andromeda's black hole. Sagittarius A star effectively becomes the lighter partner in the pair. Once a bound binary forms, the mechanisms driving orbital decay change. At larger separations, dynamical friction against stars dominates. As the binary hardens and its separation decreases, individual stars passing close to the pair can extract energy through gravitational slingshot interactions. These stars are ejected onto wider orbits, carrying energy away and tightening the binary further. This stellar scattering phase can persist for hundreds of millions of years. Its efficiency depends on the supply of stars that can interact closely with the binary. In simple models, this process can stall if the region around the binary is depleted of stars on intersecting orbits, a problem sometimes referred to as the final parsec problem. In realistic galaxy mergers, however, the situation is more complex. The merged remnant is not perfectly spherical or static. Triaxial shapes, rotating structures, and ongoing perturbations continually refill the population of stars that can interact with the binary. Gas, if present in sufficient quantities, can also contribute. Circumnuclear gas disks can exert torques on the binary, extracting angular momentum and accelerating orbital decay. As the separation shrinks to fractions of a parsec, gravitational wave emission becomes increasingly important. At these scales, the binary loses energy primarily by radiating gravitational waves, ripples in space-time, predicted by general relativity and now directly observed from much smaller black hole mergers. For supermassive black holes, this emission occurs at much lower frequencies, far below the range detectable by ground-based observatories. The gravitational wave phase lasts millions of years. During this time, the binary's orbit gradually shrinks and circularizes as energy and angular momentum are carried away. The emitted gravitational waves propagate outward at the speed of light, carrying detailed information about the masses and dynamics of the system. In the distant future, advanced space-based detectors could observe similar events in other galaxies, providing direct confirmation of this phase. The final coalescence occurs when the separation becomes comparable to the size of the black hole's event horizons. At this point, the two horizons merge into one, forming a single, more massive black hole. The process releases a tremendous amount of energy in the form of gravitational waves, briefly outshining all other sources in the universe in that channel alone. The newly formed black hole is not necessarily stationary. If the gravitational wave emission is asymmetric, which occurs when the masses or spins of the two black holes are unequal or misaligned, the remnant can receive a recoil kick. This kick can propel the black hole away from the center of the galaxy at velocities ranging from tens to thousands of kilometers per second. In the case of the Milky Way-Andromeda merger, the mass ratio strongly favors Andromeda's black hole. This reduces the maximum possible recoil velocity compared to equal mass mergers, but does not eliminate it. Depending on the spin orientations and merger geometry, the remnant black hole could be displaced significantly from the galactic center. If the recoil velocity is modest, the black hole oscillates within the central potential, eventually settling back to the center as dynamical friction drains its kinetic energy. During this phase, it may carry along a small cluster of bound stars, forming a compact, moving stellar system. Over time, this system dissolves, and the black hole returns to the center. In more extreme scenarios, the recoil velocity could be large enough to eject the black hole entirely from the galaxy. While possible in principle, this outcome is unlikely given the deep gravitational potential of the merged Milky Way Andromeda system and the unequal mass ratio of the black holes. Complete ejection would require a near maximal recoil, which depends sensitively on spin alignment. The more probable outcome is the formation of a single, extremely massive black hole residing at or near the center of the merged galaxy. Its mass would be slightly less than the sum of the two original black holes, with the difference radiated away as gravitational waves. This object would dominate the central dynamics of the remnant for the rest of cosmic history. Throughout this entire process, the black holes themselves do not pose a direct threat to stars or planetary systems. Even during the final coalescence, the region of strong gravitational influence is limited to the central parsecs of the galaxy. The vast majority of stars orbit at distances where the merger has no direct effect. The significance of the black hole merger lies not in destruction, but in its role as the final marker of galactic unification. When the two supermassive black holes merge, the last distinct cores of the Milky Way and Andromeda disappear. What remains is a single galaxy with a single central black hole carrying the combined mass and history of both systems. The merger of Sagittarius A-star and Andromeda's central black hole is therefore not an isolated spectacle, but the culmination of billions of years of dynamical evolution. It is the endpoint of orbital decay, mass redistribution, and gravitational interaction on the largest scales. Long after the spiral arms have vanished and the stellar populations have mixed, the black hole merger seals the transformation. In cosmic terms, this event is both rare and ordinary. Rare because it involves two of the nearest large galaxies to us. Ordinary because similar mergers have occurred countless times throughout the universe's history. The Milky Way Andromeda merger is not unique in its physics, only in its proximity and relevance to our own galactic future. When it finally occurs, the gravitational waves from the coalescence will propagate outward across the universe, a faint but enduring signal of a merger billions of years in the making. The galaxies will already have become one. The black holes will follow, completing the process at the deepest level gravity allows. The merger between the Milky Way and Andromeda initially acts as a catalyst for creation. In its early stages, the interaction compresses gas, destabilizes disks, and drives large-scale inflows toward dense regions. These processes favor star formation, not suppression. Gravity reorganizes matter in a way that briefly makes galaxies more efficient at turning gas into stars than they have been for billions of years. This initial starburst phase is not uniform across the merging system. It is strongest where gas densities rise most sharply along tidally distorted arms, within shocked gas layers created during close passages, and especially near the central regions where gas loses angular momentum and accumulates. The inflow of gas toward galactic centers raises pressures and densities far above their pre-merger values, pushing the interstellar medium into regimes where star formation becomes rapid and widespread. Star formation during this phase differs from the steady, regulated process seen in isolated spiral galaxies. Instead of forming stars gradually in long-lived spiral arms, the merging system forms stars in bursts, clustered in massive associations. These clusters contain large numbers of short-lived, high-mass stars. Their luminosity dominates the appearance of the galaxies, making the merger temporarily brighter and bluer than either progenitor galaxy was on its own. The efficiency of star formation increases sharply during this phase. Gas that might otherwise remain stable for hundreds of millions of years collapses on much shorter timescales. The global star formation rate of the system rises well above its long-term average. Observations of similar mergers elsewhere in the universe show increases by factors of several to 10, depending on gas content and encounter geometry. However, this surge in star formation carries the seeds of its own decline. The same massive stars that illuminate the starburst also inject enormous amounts of energy into their surroundings. Stellar winds, ionizing radiation, and eventual supernova explosions begin to heat and disrupt the gas from which they formed. These feedback processes oppose further collapse, making the environment increasingly hostile to continued star formation. As supernovae explode, they drive shockwaves into the surrounding medium. These shocks heat gas to millions of degrees, converting cold, star-forming material into hot, diffuse plasma. Some of this gas remains bound to the galaxy, forming extended hot halos. Some of it is accelerated to escape velocities and expelled into intergalactic space as galactic winds. Feedback operates not only locally, but on galactic scales. Large numbers of supernovae occurring within a short time create overlapping bubbles of hot gas. These bubbles merge and vent material out of the disk along paths of least resistance. Over time, the cumulative effect reduces the supply of cold gas available for new star formation. At the same time, the merger itself disrupts the orderly recycling of gas that sustains star formation in spiral galaxies. In isolated disks, gas flows gradually from diffuse phases into dense clouds and back again through stellar feedback, maintaining a rough equilibrium. The merger breaks this balance. Gas is either driven rapidly into stars or heated and dispersed before it can cool and collapse again. Another major contributor to gas depletion is central activity associated with the supermassive black holes. As gas flows inward during the merger, it does not all form stars. Some fraction accretes onto the central black holes, powering active galactic nuclei. Even if the activity is intermittent, the energy released can rival or exceed that produced by star formation. Active galactic nuclei influence their host galaxies through powerful feedback mechanisms. Radiation pressure, jets, and wide-angle outflows inject energy into the surrounding gas, heating it and driving it outward. This process is particularly effective in deep central regions, where gas densities are highest and gravitational binding is strongest. A GN feedback acts as a regulating mechanism. When gas supply to the nucleus increases, accretion intensifies, boosting feedback and suppressing further inflow. This self-limiting behavior prevents runaway growth of both the black hole and the surrounding stellar population. In merger remnants, AGN feedback is thought to play a key role in shutting down central star formation. As the merger progresses through successive passages, the available gas reservoir steadily declines. Some gas has been converted into stars during starburst episodes. Some has been heated into long-lived hot phases. Some has been expelled entirely from the system. The fraction of cold, dense gas capable of forming stars drops. Cooling processes become less effective over time. Hot gas in massive merger remnants can remain hot for billions of years, supported by the deep gravitational potential and continuous energy input from residual stellar and AGN feedback. Without efficient cooling, this gas does not condense into new star-forming clouds. The structural evolution of the remnant also suppresses star formation. As disks are destroyed and the system becomes more spheroidal, the conditions that favour sustained star formation disappear. Rotation-supported disks promote long-lived star-forming regions by maintaining gas in thin, dense configurations. Pressure-supported spheroids do not. Gas in these systems tends to be more diffuse and less stable against heating. The result is a transition from a star-forming system to a quiescent one. This transition does not happen overnight. It unfolds over billions of years as the cumulative effects of gas consumption, heating, and feedback take hold. Star formation rates decline gradually, then more steeply, eventually reaching very low levels. The final remnant of the Milky Way Andromeda merger is expected to be a massive galaxy with little ongoing star formation. Its stellar population is dominated by older stars formed before and during the merger. Young, massive stars become rare, and the galaxy's light shifts toward redder wavelengths as its stellar population ages. This quiet state is not a failure of gravity, but its long-term outcome. Gravity initially promotes star formation by compressing gas. Over time, the energy released by that star formation, combined with the depth of the gravitational potential, stabilizes the system against further collapse. The galaxy reaches a state where most available gas is either locked into stars or held in a hot, diffuse form. The contrast between the early starburst phase and the later quiescent phase highlights the dual role of mergers in galaxy evolution. Mergers are both creators and suppressors of stars. They trigger intense periods of star formation, then bring those periods to an end by exhausting and heating the gas supply. This pattern is observed throughout the universe. Many massive elliptical galaxies show evidence of past starbursts, followed by long periods of inactivity. Their stars carry the chemical signatures of rapid formation, while their lack of cold gas explains their present-day silence. The Milky Way Andromeda merger follows the same evolutionary path. Over cosmic time, this process contributes to the transformation of the galaxy population. Disk-dominated, star-forming galaxies merge and evolve into spheroidal, quiescent systems. The universe becomes populated with fewer actively star-forming galaxies and more massive, quiet ones as structure formation progresses. In the context of the merger remnant, quiet does not mean inert. Stars continue to orbit, age, and evolve. Stellar mass loss gradually returns some material to the interstellar medium, but not in sufficient quantities or conditions to reignite widespread star formation. The galaxy remains dynamically active, but visually subdued. The decline in star formation also marks a shift in the dominant energy sources within the galaxy. Early on, massive stars and supernovae dominate feedback. Later, low-level AGN activity and the cumulative effect of old stellar populations shape the environment. The galaxy's evolution slows, governed more by internal aging than by dramatic events. Why the remnant becomes quieter over time is therefore a matter of balance. Gravity initially drives gas together, igniting star formation. That star formation releases energy, alters the gas, and ultimately removes the very conditions that made it possible. The merger does not sustain chaos indefinitely, it moves the system toward equilibrium. By the end of this process, the merged galaxy is large, massive, and relatively calm. Its brightest days are behind it, preserved in the light of long-lived stars formed during the merger's active phases. The dramatic contrast between early brilliance and later quiet is not a sign of decline, but the natural outcome of gravitational evolution acting on gas, stars, and energy over billions of years. As the merger between the Milky Way and Andromeda approaches completion, the system enters a fundamentally new state. The oscillations fade, the last distinct cores dissolve into one another, and what remains is no longer a pair of interacting galaxies, but a single gravitationally bound structure. This moment does not occur at a sharp boundary in time. It is a gradual transition, marked by the disappearance of the features that once defined the two progenitor galaxies and the emergence of a new unified identity. The most striking transformation is the shift away from a disk-dominated form. Spiral galaxies rely on coherent rotation to maintain their thin disks and organized structures. By the time the merger reaches its final stages, that coherence has been largely erased. Repeated tidal interactions, orbital decay, and violent relaxation have redistributed energy and angular momentum throughout the stellar population. Rotation no longer dominates the system's dynamics in the way it once did. The The remnant settles into a configuration supported primarily by random stellar motions rather than ordered rotation. In such systems, stars move on a wide variety of orbits with different orientations and eccentricities. The collective effect of these motions produces a roughly spheroidal shape, depending on the residual angular momentum and the amount of gas retained late in the merger. The final galaxy may resemble either a massive elliptical or a lenticular system with only a weak thickened disk component. Elliptical galaxies are characterized by their smooth light distributions and lack of prominent disks or spiral arms. Lenticular galaxies occupy an intermediate category, retaining a disk-like shape but lacking active star formation and strong spiral structure. In the case of the Milky Way Andromeda merger, simulations suggest that the outcome is likely closer to a massive elliptical, though some rotational flattening may persist, especially if gas settles into a diffuse rotating component late in the process. The loss of disk identity is not simply the fading of spiral arms. It is the disappearance of the disk as a dynamically distinct structure. In the original Milky Way, disk stars shared similar orbital planes and velocities, giving rise to a thin, coherent system. After the merger, that shared plane no longer exists. Stars that once belonged to the disk are scattered into orbits that take them far above and below the former galactic plane. This scattering occurs through violent relaxation, a process that operates when the gravitational potential of a system changes rapidly. During the final stages of the merger, the potential fluctuates strongly as the two cores coalesce. Stars respond by exchanging energy with the evolving field, settling into new orbits that reflect the combined mass distribution rather than their original host galaxy. The result is a stellar population with a broad velocity dispersion. Instead of moving predominantly in one direction around the center, stars move in all directions with comparable likelihood. Some follow elongated orbits that plunge toward the center and back out again. Others trace box-like paths that fill large volumes of space. The memory of ordered rotation is largely erased. This randomization of stellar orbits is the defining dynamical signature of elliptical galaxies. It gives rise to their smooth appearance and their characteristic kinematic profiles. The merged Milky Way Andromeda system acquires these traits as the final stage of the merger unfolds. Any remaining gas plays a secondary role in shaping the final structure. By this point, most of the original cold gas has either been converted into stars, heated into hot halos, or expelled. If a modest amount of gas survives and retains some angular momentum, it may settle into a faint, rotating disk embedded within the spheroid. Such a disk would be thick, low in mass, and largely devoid of star formation. However, this component would not dominate the galaxy's appearance or dynamics. The overall structure would still be defined by the spheroidal stellar distribution formed through merger-driven mixing. The galaxy's light would be dominated by older stars, giving it a smooth, reddish appearance typical of massive ellipticals and lenticulars. At this stage, it becomes meaningful to speak of the new galaxy as a single object rather than a remnant of two. The name Milkomeda is often used to describe this merged system, not as a formal designation, but as a conceptual marker. It reflects the idea that the identities of the Milky Way and Andromeda have been fully subsumed into something new. Milkomeda is not simply a sum of its parts. Its structure, kinematics, and evolutionary trajectory differ from those of either progenitor galaxy. It occupies a deeper gravitational potential, hosts a more massive central black hole, and contains a stellar population drawn from two distinct formation histories, now thoroughly mixed. The spatial extent of Milkomeda is larger than that of either original galaxy. Its stellar halo extends far into space, populated by stars stripped during the merger and by remnants of smaller galaxies absorbed along the way. The distinction between inner regions, outer halo, and intergalactic space becomes more gradual, reflecting the smooth mass distribution of the remnant. The central regions are dense and dynamically hot, dominated by random motions. Toward larger radii, the density falls off and stellar orbits become more elongated and loosely bound. These outer regions preserve some memory of the merger in the form of faint streams and shells, but even these features fade over time as phase mixing smooths them out. The formation of Milkomeda represents the end point of major structure formation within the local group. With the Milky Way and Andromeda merged, no other galaxy in the group rivals the remnant in mass. Smaller satellites are either absorbed over time or remain as distant companions on long, slowly evolving orbits. From a cosmological perspective, this transformation occurs against a changing backdrop. As dark energy drives the accelerated expansion of the universe, distant galaxies recede beyond the observable horizon. Over very long timescales, Milkomeda becomes increasingly isolated, surrounded by emptiness rather than neighbouring galaxies. This isolation reinforces the quiet nature of the remnant. Without frequent interactions or fresh infall of gas from the cosmic web, Milkomeda evolves passively. Its stars age, its stellar populations redden, and its overall luminosity declines gradually as short-lived stars disappear. Yet the galaxy remains dynamically alive. Stars continue to orbit the centre, interacting gravitationally and slowly redistributing energy. The central black hole exerts its influence on nearby stars. Stellar remnants accumulate. The system evolves, but it does so internally, without the dramatic external drivers that shaped its formation. The birth of Milkomeda is therefore not an explosion or a sudden event. It is a settling. The violent motions of the merger subside, replaced by a stable, long-lived configuration. The chaos of interaction gives way to equilibrium. In this sense, Milkomeda is the mature outcome of the processes that began with the formation of the local group. Gravity drew matter together, built two large spiral galaxies, and then brought them together again into a single, more massive system. The merger does not end galactic evolution. It changes its mode. The transition into a massive elliptical or lenticular galaxy reflects a universal pathway in cosmic history. Many of the largest galaxies in the universe are thought to have formed through similar mergers. The Milky Way-Andromeda merger is not exceptional in its physics, only in its proximity and relevance to our own cosmic neighbourhood. The loss of disk identity, the randomization of stellar orbits, and the emergence of a unified structure mark the completion of this transformation. Milkomeda stands as a single galaxy, carrying within it the stars, remnants, and histories of both progenitors, bound together by gravity and shaped by billions of years of interaction. What began as two rotating disks separated by millions of light years ends as one massive, quiet galaxy. The process is slow, cumulative, and governed by the same physical laws that shape galaxies across the universe. In the end, Milkomeda is not a catastrophe or an anomaly. It is the natural consequence of gravity acting patiently on cosmic scales. After the Milky Way and Andromeda complete their merger, the local group is no longer a collection of comparable members. Its structure simplifies dramatically. What remains is a single dominant galaxy surrounded by a diminishing population of much smaller companions. The transformation from a loose group into a system centered on one massive remnant is a natural consequence of gravity acting over long timescales, amplified by the changing conditions of the expanding universe. Before the merger, the local group contains dozens of galaxies. Most are dwarf systems, ranging from relatively luminous dwarf ellipticals to ultra-faint satellites barely holding themselves together. These galaxies orbit within the shared gravitational potential dominated by the Milky Way and Andromeda. Their future is tied to the evolution of that potential, and once the two largest members merge, the fate of the smaller ones becomes increasingly constrained. The merged galaxy, often referred to as Milkomeda, possesses a total mass far greater than either progenitor alone. Its dark matter halo deepens and expands, extending its gravitational reach. Satellite galaxies that once orbited the Milky Way or Andromeda separately now find themselves moving within a single, more massive halo. Many of these satellites are already on decaying orbits, gradually losing energy through tidal interactions and dynamical friction. Over billions of years, the absorption of satellite galaxies continues. Each satellite experiences tidal stripping as it orbits the central remnant. Stars are pulled away first, forming faint streams that wrap around the halo. Gas, if present, is removed even more efficiently. What remains of the satellite shrinks with each orbit until it is fully dissolved into the stellar halo of the central galaxy. This process is slow and hierarchical. Larger satellites survive longer, completing many orbits before being fully disrupted. Smaller and more fragile systems dissolve quickly, sometimes in a single close passage. The end result is a smooth, extended halo populated by stars that once belonged to many distinct galaxies. These accreted stars preserve subtle records of their origins for some time. Their chemical compositions and orbital properties differ slightly from those of stars formed in the central galaxy. Over very long timescales, however, phase mixing erases these distinctions. The halo becomes dynamically and chemically smoother, and the memory of individual satellites fades. One of the most important remaining members of the local group after the Milky Way Andromeda merger is the Triangulum galaxy. Triangulum is significantly smaller than either of the two giants, but much larger than typical dwarf galaxies. Its fate is closely linked to its orbital history and its gravitational relationship with Andromeda. Current evidence suggests that Triangulum is gravitationally bound to Andromeda, or at least strongly influenced by it. As Andromeda merges with the Milky Way, Triangulum is drawn into the evolving gravitational field of the combined system. Several outcomes are possible, but all involve Triangulum losing its independence over time. In some scenarios, Triangulum merges with Andromeda before the Milky Way. Andromeda merger is complete. In others, it survives the early stages and becomes a satellite of the merged remnant. Even in this latter case, its long-term future is similar to that of other satellites. Tidal forces strip its outer regions, and dynamical friction slowly shrinks its orbit. Because Triangulum is relatively massive, it can persist for several billion years as a recognizable galaxy. However, it is unlikely to remain intact indefinitely. Over time, it too is absorbed, contributing its stars, gas, and dark matter to the growing remnant. The local group thus loses its last large secondary galaxy. As this process unfolds, the structure of the local group simplifies. Instead of a handful of moderately large galaxies and many dwarfs, there is one overwhelmingly dominant central galaxy and a sparse population of much smaller companions. The term group becomes less descriptive. The system more closely resembles a massive galaxy with an extended halo of satellites than a true multi-member group. This reduction is not driven solely by mergers. The broader cosmological environment plays a critical role. As dark energy accelerates the expansion of the universe, the large-scale cosmic web thins out. Regions that are not gravitationally bound drift apart at increasing rates. For the local group, this means that it becomes increasingly isolated from other galaxy groups and clusters. Galaxies beyond the local group recede faster and faster, eventually crossing the cosmic event horizon. After this point, light emitted from them can never reach the local group again. Over tens of billions of years, the observable universe from within Milkomeda shrinks dramatically. Distant galaxies fade from view, not because they cease to exist, but because space itself expands too quickly for their light to keep up. This accelerated expansion has a stabilizing effect on the local group remnant. No new large galaxies fall in from outside. The supply of fresh material from the cosmic web effectively shuts off. Milkomeda evolves in isolation, shaped only by its internal dynamics and the gradual accretion of its remaining satellites. The long-term isolation has profound consequences for galactic evolution. Without new gas inflow, star formation continues to decline. The stellar population ages. The galaxy's appearance becomes smoother and redder. Dynamical processes continue, but they operate entirely within a closed system. Over extremely long timescales, even the remaining satellites are either absorbed or pushed onto wide, stable orbits where tidal effects are weak. The central galaxy dominates the gravitational landscape completely. The local group, once a modest assembly of galaxies, effectively collapses into a single enduring structure. From within this future galaxy, the sky looks very different from today's. There is no nearby Andromeda, no triangulum, no surrounding population of bright neighbours. The sky is dominated by the stars of the central galaxy, and perhaps a handful of faint satellites. Beyond that, there is darkness. This isolation is not unique to the local group. It is the expected fate of all gravitationally bound systems in an accelerating universe. Galaxy clusters retain their members, but drift away from one another. Smaller groups like the local group lose their external context almost entirely. In this future, Milkomeda becomes a kind of cosmic island. Its internal history remains rich and complex, shaped by billions of years of mergers and interactions. Externally, however, it exists alone, separated from the rest of the universe by ever-expanding space. The transformation of the local group after the merger therefore reflects two intertwined processes. One is local and gravitational, the absorption of satellites and the consolidation of mass into a single dominant galaxy. The other is global and cosmological, the accelerated expansion that isolates bound systems from one another. Together, these processes mark the end of an era of structure formation for the local group. The dynamic youth of the group, defined by interactions and mergers, gives way to a long period of quiet evolution. The local group does not disperse, it condenses and then becomes isolated. What remains is not emptiness, but permanence. A single massive galaxy, carrying the combined mass and history of many others, persists while the rest of the universe recedes beyond reach. The local group's future is not one of continued growth or interaction, but of long-term stability in an increasingly empty cosmos. When viewed from a sufficiently large scale, the merger between the Milky Way and Andromeda is not a special event. It feels exceptional only because it involves the galaxy we inhabit and the nearest large galaxy we can see. In the broader context of cosmic history, it is a routine outcome of how structure forms and evolves in the universe. Galaxy mergers are common. They are not rare accidents or anomalies. From the earliest epochs after the first galaxies formed, gravity has been assembling matter hierarchically. Small structures form first, then merge to create larger ones. This process has operated continuously for more than 13 billion years. Every massive galaxy visible today is the product of many mergers, most of which occurred so long ago that their signatures are now subtle or erased. Observations across cosmic time confirm this picture. Deep surveys show galaxies in all stages of interaction, pairs approaching one another, systems in mid-merger with distorted shapes and tidal tails, and smooth remnants that bear little resemblance to their progenitors. At earlier times in the universe, mergers were even more frequent. Galaxies were closer together, the universe was denser, and relative velocities were lower, making gravitational capture easier. In that sense, the Milky Way has been unusually quiet in recent cosmic history. While it has absorbed many small satellites, it has avoided a major merger for billions of years. Andromeda, by contrast, shows clearer evidence of past large interactions. The upcoming merger is not a deviation from cosmic norms, but a delayed example of a process that has shaped galaxies everywhere. On cosmic scales, the Milky Way-Andromeda collision is therefore ordinary. It follows the same physical principles, timescales, and outcomes seen in countless other mergers. The galaxies approach because they are bound, they interact because their halos overlap, they merge because orbital energy is dissipated gradually. The remnant becomes larger, more massive, and dynamically hotter than its progenitors. Nothing about this sequence requires exotic physics or unusual conditions. What gives mergers their dramatic reputation is appearance, not mechanism. Interacting galaxies look violent, their shapes are distorted, their gas glows brightly, their star formation rates spike, and their structures appear chaotic. From a distance, these systems resemble cosmic wreckage. This visual violence, however, can be misleading. The underlying physics of galaxy mergers is gentle. Gravity acts smoothly and predictably. Accelerations are small. Forces are weak compared to those encountered in everyday life. Even at closest approach, the gravitational field experienced by individual stars changes gradually over millions of years. There are no sudden shocks for stars, no impacts, no explosions at the scale of stellar systems. The apparent contradiction between violent visuals and gentle physics arises from scale. When processes operate over hundreds of thousands of light years and billions of years, even mild forces can produce dramatic rearrangements. Gas clouds collide, compress, and heat, creating luminous phenomena. Stars respond to changing potentials by shifting orbits, producing large-scale distortions. The system looks turbulent because enormous numbers of objects are responding collectively, not because any one object is experiencing extreme conditions. This distinction is crucial. Galaxy mergers are not destructive in the sense of breaking stars apart or destabilizing planetary systems en masse. They are transformative at the level of structure, not constituents. They reorganize matter rather than destroy it. The outcome of this reorganization reflects a deeper trend in cosmic evolution, the universe's tendency toward fewer, larger structures. Early on, matter was distributed relatively evenly, with small fluctuations. Gravity amplified those fluctuations, drawing matter into increasingly massive concentrations. Over time, small halos merged into larger ones, and galaxies merged into larger galaxies. This process does not continue indefinitely. As structures grow, their relative abundance decreases. There are many small galaxies and few very large ones. Major mergers become less frequent as the universe expands and matter becomes more diffuse. The Milky Way-Andromeda merger occurs near the end of this hierarchical process for the local group. The accelerating expansion of the universe reinforces this trend. Dark energy causes unbound regions to separate faster over time, reducing the likelihood of new mergers between distant systems. Bound structures like the local group complete their internal mergers, then become isolated. Growth gives way to consolidation. In this future, the universe contains a population of large, isolated galaxies or galaxy clusters, each evolving largely on its own. The era of frequent mergers ends not because gravity stops working, but because expansion stretches space faster than gravity can draw new structures together. Milkomeda, the remnant of the Milky Way-Andromeda merger, fits naturally into this picture. It is not the beginning of something unprecedented, but the conclusion of a long sequence. It represents the final assembly of mass within the local group, after which no comparable partners remain to merge with. From a cosmological perspective, this merger is therefore both ordinary and terminal. Ordinary because it follows the standard pathway of structure formation. Terminal because it marks the end of that pathway for this region of the universe. The contrast between how mergers feel to observers and what they represent physically highlights a recurring theme in cosmology. Many of the universe's most dramatic phenomena are governed by simple, well-understood laws acting patiently over immense scales. Gravity does not rush, it accumulates effects. The Milky Way Andromeda collision does not signal chaos at the largest level, it signals order playing out. Matter follows the contours of gravitational potential. Energy is redistributed. Structures settle into more stable configurations. Seen this way, the collision is not an anomaly or a disaster. It is the universe doing what it has always done, simplifying complexity by gathering mass, reducing the number of independent systems, and moving toward long-lived equilibrium states. In the distant future, long after the merger is complete and the local group has become an isolated island in an expanding cosmos, the event itself will leave little obvious trace. The tidal tails will fade, the stellar streams will mix. The memory of two separate galaxies will exist only in the motions and compositions of stars, detectable only to careful analysis. What remains is a single galaxy, shaped by a process that has occurred billions of times across the observable universe. The Milky Way Andromeda merger matters to us because of where we live. To the universe, it is simply one more step in the quiet, persistent tendency of gravity to turn many things into fewer, larger ones.